Hi guys, in this video we'll be covering some miscellaneous examples on limits. So let's start with our first example. Let's suppose f of x is defined by this definition, that is a plus bx when x is less than 1, and it is 4 when x is equal to 1, and it is b minus ax when x is greater than 1. And along with this, if x approaches to 1, limit f of x is given as f of 1. Then find the value of a and b. So this is our question. So now let's start with the solution. Let us think how we will approach in this problem. Now since this limit x approaches to 1, f of x is given as f of 1. Then what is f of 1? So you can see from here it is equal to 4. Okay. So now this thing, limit x approaches to 1, f of x, since it is equal to a finite number, that means it exists for sure. And it is equal to 4. So in our case, that means the left hand limit for x approaches to 1 as well as the right hand limit for x approaches to 1 will exist, right? So now let's first compute the left hand limit when x is approaching to 1. So that will be limit x approaches to 1 negative f of x, right? So now here 1 negative means the value of x is less than 1 but very close to 1. So which definition will satisfy from these definitions? That will be this one. Since for x less than 1, we take this definition of f of x. So this definition we will take for values of x less than 1, or we can say 1 negative. So we can write it as f of x is equal to a plus bx here, right? So now since x is approaching to 1 negative, so the approximate value we can plug in this is 1. So we will plug in 1 here. So that will be a plus b. So the left hand limit is coming as a plus b. Let us mark it as 1. Now we'll compute the right hand limit. So the right hand limit will be limit x approaches to 1 positive f of x. Now in this case, for x approaches to 1 positive, we have x is greater than 1, since the value of x is approaching 1 but it is greater than 1. So this definition will be our consideration. So that will be this will be b minus ax. So we will write it as limit x approaches to 1 positive b minus ax, right? So this will be, now we can plug in x equal to 1 since it's approaching to 1. So approximately we can plug in 1. So now that will be b minus a. Now let us mark it as 2. So now for the limit to exist, the LHL should be equal to the RHL. And since it is given in the question that also that the limit is existing and it is equal to a finite quantity, and that is 4. So both the left hand limit and the right hand limit will be equal. So from these deductions we can write a plus b is equal to b minus a, and it is equal to f of 1. Now what is f of 1? This is nothing but equal to 4. And so we have two equations with us. A plus b is equal to 4. Let's mark it as 3. And b minus a is also equal to 4. Let's mark it as 4. So now we have to solve these two equations. So now let us solve in order to find the values of a and b. So from equation number 3, we have a plus b is equal to 4. And a plus b minus a is equal to 4. So let's write it as minus a plus b, and this is also 4, right? from equation number 4. So I'm just rearranging for making pair of A and B, right? Okay, so these are our two equations. So now let's solve this. So we have to evaluate one variable from here in order to find the value of the other variable. So let us first add these two equations. So when we add, this minus a gets cancelled with this a and b gets added with this b. So this becomes 2b equals 8. So if 2b is equal to 8, this implies that b is equal to 4. So we have found the value of b is equal to 4 now. So how we will now find out the value of a? We will plug in the value of b in any of these equations. So now let's plug in b is equal to 4 in this equation. So that is a plus b is equal to 4. So that will be a plus 4 equal to 4. So this means a is equal to 0. So hence we are able to find out the values of a and b. And our answer is b is equal to 4 and a is equal to 0. Right. So this is our answer. Now let's take another example. In this example, we have to evaluate limit x approaches to 0 root over 1 plus x minus 1, and this one is not under root, and this whole thing is divided by x. So we have to evaluate limit at x approaches to 0. So now let us try to plug in x equal to 0 in the numerator as well as the denominator. So if we plug in, so our answer will come as root over 1 plus 0 minus 1 over 0. So this is root of 1 is 1 and 1 minus 1 is 0 over 0. So this is 0 by 0, which is an indeterminate form, as you might be knowing now. So this is indeterminate. So how we will evaluate? So here one thing we can do, that we can multiply in the numerator and the denominator with the conjugate of this numerator. Okay, so let's try to do this once. So then it will be more obvious to you that why I have done this, right? So the conjugate will be root over 1 plus x plus 1. So the sign between the two terms will get reversed. So in order to find the conjugate. So now let's multiply this whole with root over 1 plus x minus 1, sorry, 1 plus x plus 1 in the numerator and the denominator. So this will come as limit x approaches to 0 root over 1 plus x minus 1 multiplied by its conjugate, right? So that will be under root 1 plus x plus 1, and the denominator it will be x multiplied by under root 1 plus x plus 1. Okay. Now you can see an identity here. Let's say this is a and this is b. So this is a minus b and this is a plus b. So by the identity, a minus b multiplied by a plus b is equal to a square minus b square. So this is the identity. So we will use this identity in order to make this simpler. So let's do that. So this will be limit x approaches to 0, a square, that is this square will be root of 1 plus x whole square, that will be 1 plus x minus b square, that is 1. So over x multiplied by root of 1 plus x plus 1. So this one gets cancelled with this one, and this, the remaining part which is x, gets cancelled with this x. Since x is approaching to 0, it is not equal to 0. So we can cancel this x. So the remaining part is limit x approaches to 0, 1 over under root 1 plus x plus 1. So now let's try to plug in x equal to 0 here. So if you plug in x equal to 0, this will be root over 1 plus 0, that is 1. And so it will be 1 over 1 plus 1. So that will be 1 by 2. So now we are able to get the answer, that is 1 by 2. So just by multiplying the numerator and the denominator with the conjugate of this thing, this numerator, we are able to solve for the limit. So had this thing been in the denominator also, we still would have done the same thing, right? So this was the example when we had to multiply with the conjugate in order to make our example computable for limits, right? Let's start with our third example now. So let's say we have a function f of x is equal to greatest integer of cos x, and we have to find limit x approaches to pi by 2 f of x. So first of all, I will make your understanding more clear about this greatest integer x part. So let us say this is not cos x. Let's assume first we have another function. Let's say gx is equal to let's say gx is equal to greatest integer x. I'll make your understanding clear about this greatest integer x part first. Then we will go on to compute the limit, right? So the graph of greatest integer x is something like this. So this is like a step function, right? As you can see. Now, let's say we have to compute greatest integer of 1.23. So let us take this value, and this value will be somewhere lying here. So the y coordinate will be 1. So the greatest integer of 1.23 will be 1. Similarly, let us take greatest integer of minus 0.32. So for this, the x value will be lying somewhere here, and the y coordinate will be lying on this branch. So that will be minus 1. So the greatest integer of minus 0.32 will be minus 1. Let's take another example like minus 1.52. So minus 1.52 will lie somewhere here, and the y coordinate will be on this branch, and that will be equal to minus 2. So this was for giving you the basic understanding of how the greatest integer of x behaves. So now let's try to draw, or you can say let us try to compute this limit x approaches to pi by 2. Now this pi is in radians, so pi by 2 will be equivalent to 90 degrees. So let us try to first draw the graph of fx is equal to cos x. Okay, so first I will draw the graph of cos x. So cos x is plotted something like this, something like this. Okay, and this is 0, this is pi by 2, this is pi, this is 3 pi, this is 3 pi by 2, and so on. And this is minus pi by 2, right? And this part, this y coordinate is 1 and this y coordinate is minus 1, since cos x will always range between minus 1 to positive 1. So now we will proceed to compute the limit x approaches to pi by 2 f of x. And f of x is greatest integer cos x, right? So now in order to find the limit, in order for the limit to exist, we have to make sure the left hand limit at this point is equal to the right hand limit at this point. By the concept of existence of limits, we have to make this point clear. So let's say first we compute the left hand limit. So the left hand limit will be limit x approaches to pi by 2 negative f of x. And so it will be limit x approaches to pi by 2 negative greatest integer of cos x. Now let's see from the graph, x approaches to pi by 2 negative means value of x close to pi by 2 but less than pi by 2. So we will approach from this side. Okay. So in this thing, the value is, if we see from the graph, the y coordinate, the value is very close to 0, but it is a positive quantity, right? So let's say this is a very small quantity. Let's say h, and we can represent from the graph that it is a very small quantity. Let's say that is uh, equal to h, right? So this we can replace this as uh, since we are using h here, so we can say h is approaching to 0, and h is a very small positive quantity. So the greatest integer of this this thing we have to compute. So so limit x approaches to 0, the greatest integer of h we have to compute. So let's say we take a very small value, let's say 0.001 or 0.0001, any small value. So the greatest integer we can compute from this branch. The value of h will lie somewhere here. So the greatest integer will come as 0. That is, limit x approaches to 0, greatest integer of h is coming as 0. So the left hand limit is coming as 0. Now we will try to compute the right hand limit. Okay. Uh, so let's compute the right hand limit. The right hand limit, that is the RHL, will be equal to limit x approaches to pi by 2 positive greatest integer of cos x. Now from the graph, as you can see that when x approaches to pi by 2 positive, that means we are approaching from somewhere here. So we are approaching from this side, right? And the value of x is very close but greater than pi by 2. So the value will somewhere lie here, somewhere here. Okay, so the y coordinate will be less than 0 but greater than -1. Since the y coordinate will lie somewhere here in this region. So it will be less than 0 but greater than -1. So this thing we can rewrite as, since it is a very small negative quantity, let's say it can be represented as minus h. H is a very small positive quantity, so minus h will be a very small negative quantity close to 0. So our y coordinate we can represent by this. So we can replace this whole limit as limit h approaches to 0, greatest integer of minus h. So this thing we deduce from the graph. Okay, so now let's take use of these examples to compute uh, greatest integer of minus x. These examples here. So when h is very close to 0, right? Let's say we have minus 0.01 or minus 0.32 like here, or minus 0.002, somewhere like this. So something like that. Okay, so our x coordinate will lie somewhere here, right? Somewhere here. So our y coordinate corresponding to this x value will be -1. Since so the y coordinate comes as -1. So the limit greatest integer of minus h when h is approaching to 0 will be equal to -1. So this is coming as -1. Okay. So now the left hand limit was equal to 0 and the right hand limit is coming as -1. Now since the left hand limit and the left hand limit and the right hand limit, they both are not equal to each other, then we can say surely that the limit does not exist. So thank you guys. Bye bye.